Yes, the subject of these lectures will be topological order, and in these lectures we will analyze several examples of topologically ordered systems to make you understand what topological order is, and we will also investigate the intimate connection between topological order and quantum computation. Essentially, I will aim to show you how topological order can improve our life if we want to build a quantum computer. In these lectures, I will act like a thief. Essentially, we will steal some ideas that you already have seen in the previous lectures and apply them in a new way to understand what topological order is and to analyze topologically ordered system. This is because many people consider topological order like a new sort of paradigm for the study of phase transitions in general, and I don't know if this statement is really accurate because of course topological order is based on elements that were already present in physics due to lattice gauge theories and other stuff, but I think that it is almost safe to assume that before the discovery of the quantum Hall effect at the beginning of the 80s, the condensed matter community believed that all the phase transition may be explained through the Landau-Ginzburg theory. And essentially, we know that the Landau-Ginzburg approach is based on two main elements to understand the phase transition. The first one is the analysis of the symmetries of the system. Essentially, you have seen many examples of Hamiltonians, and these Hamiltonian have some sort of symmetry and depend, for example, from some parameter like the temperature. And you vary the temperature, and you observe that on a certain phase, the ground states or the usual the system obeys the same symmetry of the Hamiltonian, but at a certain point you hit a phase transition, and after this phase transition you have some sort of symmetry breaking, so that the ground state or your system in general does not obey anymore the symmetry which is present inside your Hamiltonian. And to understand this phase transition, usually you have seen that one introduces local order parameters, which are fields usually. For example, you have seen, I guess, the Ising model, or yesterday, as there was speaking about the XX model, and the analysis of the expectation value of this local order parameter may tell you whether you are in some ordered or disordered phase. Well, in the case instead of topologically ordered system, this is not true anymore. Essentially, the discovery of quantum Hall physics shows that it is possible to have phase transition even in the absence of symmetry, when your Hamiltonian does not have any particular symmetry, and that essentially local order parameters are not enough to understand this new kind of phase transitions. And well, for example, you already saw yesterday in the lecture by Sierra that introduced some new kind of order parameter which he called the string order parameter, which was present in the Aldane spin-1 model with the equality state. And we will see that also topological order must be understood in terms of string order parameters, but still there is something more. There is the role of topology. And I will try to explain you how topology enters in this picture of phase transitions and in general in the characterization of topologically ordered phase. Essentially today we will speak about the toric code, which is in my opinion the best and the easiest example of a topologically ordered system. And my aim for this lecture will be to explain you the definition of topological order in such a way that in the end you will understand it through the example of toric code. Then the other 2 lectures will be devoted somehow to the study of non-abelian anyons in general, which are quasi-particles living in 2-dimensional systems which do not obey neither the fermionic nor the bosonic statistics. And finally, we will explore the physics of Majorana modes in topological superconductors, which is a very hot topic in the recent years, and in my opinion it is one of the best understood physical case of non-abelian anyons, even though you cannot fully consider them non-abelian anyons, but this is just a detail. So let us start from the study of toric code, but before I would like to emphasize that all these 3 topics have a strong connection with quantum computation. And to understand why the topological order is useful to the purpose of quantum computation, you may think what are the most desirable characteristics that a system must have in order to encode quantum information, in order to have a qubit. So if you want to engineer a quantum computer or a quantum memory, usually you try to have a spectrum in energy which is somehow of this kind. You will have a set of degenerate or almost degenerate ground states that are separated with a big gap from all the other states in your theory. And this gap essentially provides the first protection of the information that you want to encode in this small portion of the hyperspace. So essentially you want to work really only on this part of the hyperspace, and you know that if your gap is big enough in such a way that noise that you cannot control or temperature is much lower than this energy scale, it is very difficult for the system to jump from these computational states that are protected to the non-computational excited states that somehow may be treated as errors. The second level of protection that you want to acquire when you engineer a quantum memory is meant to avoid unwanted transitions from the states inside the protected space. So you don't want to have noise or operators acting on your system in an unpredictable way, which may allow a tunneling from the state 0 to the state 1. And usually this protection is achieved through the presence of symmetries in your Hamiltonian. Instead, in the system that we are going to analyze today, this protection will be achieved through some topological characteristic, and we will check better later. So I spoke a lot about topological order. And let me give you a first definition, a definition of topological order. This is a pretty strong definition, and it is the one usually used by Kitaev. So the requirement 0, let us say, is the previous one for the gap. Essentially, you want to have a set of low-lying energy states or ground states that are separated by a big gap from all the excitations in the system. So once you have fulfilled this requirement, you may ask how this degeneracy of the ground states depend on the physical properties of the system. And the key point is that the number of degenerate ground states must depend only on topological properties of the system, namely on the boundary condition or on the presence of holes in our system. Essentially, this definition works fine in 2-dimension, and if you consider a 2-dimensional system, you may consider either the boundary conditions that are typical of a torus or a cylinder, and so it is easy to understand that if I have a cylinder or a torus, this method have a different number of holes, and we will see that through different boundary terms we will obtain a different number of degenerate ground states. But on a more realistic point of view, we may also consider simply a plane and consider to cut some hole in the plane and keep the Hamiltonian working everywhere else. And we want to achieve essentially a system in which the number of ground states depends on the number of holes. In both cases, we may summarize this characteristic of the number of holes inside your space as the genus of the manifold. So, the first thing is that the number of ground states must depend only on this sort of characteristic of your system. And the second and most important point is the one that gives you the protection I was speaking before, is that no local operator must distinguish between the different ground states. Essentially, if you act with an operator or with a local observable, you should not be able to detect whether your ground state is in a state psi I or in a state psi B. This relation may be true also up to some correction, let us say. So we have psi alpha or psi beta, and I want this to be proportional to some constant and delta alpha of beta, plus I may tolerate something that scales like the system dimension, so that once we consider the thermodynamic limit of the system, this relation becomes exact. So this is telling me that if I measure through a local measurement of the system here, I cannot detect whether the state is psi A or psi B, and most importantly, if I act with a local operator here, I cannot obtain a transition between psi I and psi A. It is important for us that I define what I mean with local in all of this, and essentially if you consider a system like the one that we are going to analyze, which is a spin system on a square lattice, you may, so imagine to have a square lattice, and to have spin 1/2 on each edge of this lattice. Then I will define some compact support given by some sort of radius. So I take a radius R, and I say that an operator is local if all the elementary operators that contribute in defining it are at a distance on my physical space which is smaller than R. So if I apply operators that are based on these 4 spins, then this is a local operator, and it must not be able to allow transitions from states. Instead, a non-local operator is something that involves spin that are very different, that are distant enough, let's say. I want essentially this radius not to scale with the system dimensions. And so these are the 2 main points, the essential points which define a logically ordered phase. And I will add here a third element, which is very intriguing. And usually in all these topologically ordered systems, we have as low energy excitations over the ground state that there appear some anion, which are essentially localized quasi-particles which do not obey either the fermionic or the bosonic statistics. Essentially, these are necessary conditions for having anions. I don't believe that they are also sufficient.
Excuse me, regarding the point number 2, no local operator can distinguish between different. If you have a global translation, you also want that it does not distinguish different cogenitive state, or in that case it could be that it causes
yeah, I would say that the global translation in general is a non-local operation, but so it should not. It could in principle sound
without spoiling the topological order.
No. So I don't have an example here of a system which spoil its topological order through translations, but in principle I cannot exclude that. I have to think better about it. We see in the last lecture about essentially the K-type chain, and in that case a transition one may be interpreted as a transition between the topological and the non-topological phase, but still all these systems rely on some sort of boundary conditions, so they do not behave really well under translation. So we have to discuss that more. So, before starting really to write down the Hamiltonian rhetoric code, I want to warn you that there are two possible approaches to this problem. The first approach is the more condensed matter approach to the rhetoric code, which means that we will deal with the rhetoric code as a physical system specified with an Hamiltonian. And in my opinion, this is one of the is essentially the original way of thinking about it, and the objective behind this approach is to be able to build a self-correcting quantum memory. Essentially, if you think about classical computation, you see that your bits are usually encoded in magnetic domains, and all these magnetic domains are in a ferromagnetic phase in such a way that if a single spin flips, you acquire some energy, and interactions with the neighboring spins try to flip it back in the original state. So the classical memories usually can be seen as self-correcting memories. And the aim of K-type was to obtain something like that also for quantum systems at 0 or low enough temperature. We see that this approach essentially fails because for the rhetoric code, if we switch on the temperature, we spoil the information that we want to preserve. But still, this Hamiltonian approach is very effective to understand the behavior of this system and the definition of topological order. The second approach is instead slightly different, and it consists in looking at the rhetoric code as a quantum error correction code. This is why it is called a code. Such a way that we will see the terms in the Hamiltonian must not be interpreted like a real interaction in your system, but as a set of measurements that you have to apply to your system to be sure that no error occurred during the computation, and to be sure that essentially the information that you put inside the system at the beginning is still surviving without looking at this information. So let us start from the first and most simple approach, which is the Hamiltonian approach. As I said, the rhetoric code is defined always in, well, not always, but it is usually defined on a square lattice, and there are spin 1/2 which live on the edges of this spin lattice, so that usually you may apply whatever spin 1/2 operator you want on these physical spins. And the Hamiltonian is written in terms of the sum of two sets of operators. The first set that I define A operator or star operator is the product of 4 sigma x Pauli matrices which surround a vertex of the square lattice. And well, we will see that it corresponds to looking essentially on the presence of a charge in this vertex or in the absence of a charge. And the second term instead, I call it B or bracket term, is the product of 4 sigma z operators on the 4 spins surrounding a single square bracket. The important thing about these terms is that all of them commute. That's because if they are far enough, you see that they have no spin in common, so all the single operators that compose these A and D operators commute to each other. And if instead they become close to each other, I have an even number of crossings essentially. So if you calculate the commutator, you have 2 different anti-commutations, 2 minus 1 signs, which simplify, and you obtain that A and B commute. So this is very useful because it means that I can essentially diagonalize this Hamiltonian by specifying all the values of these operators A and B, which in principle may assume the two eigenvalues +1 or -1, and to specify the ground states. Each ground state must minimize this energy, so all the A's and all the B's must have an eigenvalue +1. So this is the condition to minimize the energy. However, we must consider what is the number of ground states in such a system. And essentially, here it enters the role of the boundary conditions. Here, these black dots reminds you that essentially we are on a torus. This edge is equal to that edge, and this edge corresponds to this other edge. And if you are on the torus, beside these two constraints, beside these two conditions which minimize the energy, you have also to consider that there are two constraints that characterize these operators. Essentially, the product of all the A's is equal to 1, and the product of all the B's is equal to 1. This is because if you consider the product of subsequent vertex operators, like this one, and then I take the one centered here, this one, I am applying twice sigma x, and of course sigma x squared is equal to 1. And if we continue to multiply by all the operators A, you obtain that each spin on each edge is taken twice, and thus we obtain exactly the next. And the same is true for the plaquette. So in this system, we have essentially this number of physical spins, and we are fixing all this number of constraints. So we are fixing that all the A's are equal to 1, which amounts to fixing L² constraints. The same is true for B, but however, once we fix L² minus 1 plaquette operator, we have that the last one is already given because of this relation. So if you count the number of ground states which satisfy this constraint, you obtain that the number of ground states is 4, because you have 2 to the n is the number of it's a basis of my Hilbert space for this system, where n is the number of total spins, minus the number of constraints that I'm fixing by requiring the minimization of the energy, but there is also this dependency of the commutators. And so you obtain that there are 4 states which satisfy the minimization of the energy. So there are 4 ground states, and I will try to explain you how these ground states may be manipulated or at least understood. To do this, we must ask what are instead the highest energy states, and essentially we obtain that there are 2 sorts of excitation. Let us start from a ground state, and let us imagine to apply a sigma z operator centered on this edge. At this point, you see that this sigma z does not commute with this operator A and with that operator A, because the A are defined in terms of sigma x. So, if at the beginning A is equal to 1, once I apply this sigma z operator, this vertex operator A becomes equal to +1. And I identify this +1 as a localized excitation of this vertex that I call an electric charge E. And this terminology is motivated from lattice gauge theory. The same is true also for the plaquette terms, in which I may apply an operator x to the ground state on a single edge, and I excite 2 different excitations. So I violate 2 of these constraints that tells me that B must be equal to 1. In this case, these 2 plaquettes acquires a sign which is -1, and I interpret this as the presence of a magnetic flux inside this plaquette. This thing of electric charges and magnetic vortices essentially is to the fact that we will see there are RF phases which appear once we move these excitations one around the other. But the important thing is that once you apply a single elementary operator like sigma x or sigma z, you are creating pairs of these excitations, and the energy of the system becomes essentially 4, because each excitation has an energy 2 over the ground state, and you are creating always pairs of excitations.
Could you write down the ground states?
Sorry?
Can you write down what the ground states are?
Yes, you can, and we will discuss it in one. So essentially, well, no, it's better if you see it afterwards. But the main characteristic is that it has a very long range entanglement, so it is very strongly correlated as a ground state. All the ground states are. But before going there, I would like to consider what happens when we apply strings of these operators z or x. So we saw that if we start from one of the ground states and we apply a sigma z, we obtain 2 of these electric charges. Now, if I apply a sigma z close to the first one, I obtain that the vertex operator here in the middle has essentially 2 terms which are commute with it, and it's flipped back to a value +1. So now the two vertex operator A that I am violating are in this position and in that position. And essentially, if I continue to add sigma z operator in order to define a string of the edges of this lattice, I obtain that I am moving the second particle on the vertices of the lattice, so that I can go on and on and on and on until I may close the loop. And once I close the loop, you see that all these A operators commute with this string of z's, because you have one entering z and one exiting z from each vertex, so an even number of them, and you obtain that this is a symmetry of the Hamiltonian, because it does not change the energy. Actually, we can say that this symmetry is the product of 4 B operators, because if you consider this as taken twice, so I add sigma z and sigma z, sigma z and sigma z, this decomposes in the product of 4 plaquette operators, where the inner edges do not really are not important, since I am applying twice polymetrics on them. And so these Z strings create nucleate pairs of electric charges, move them around, and if I close the loop, they annihilate the charges in such a way that they are symmetries of the system. The same is true on the dual lattice for the magnetic fluxes. Essentially, as I said, if I apply a single X operator on one edge, I obtain a pair of magnetic fluxes, but then I can continue to add these X operators, and you see that this plaquette term is restored, because I am applying 2 different sigma X, and this product commute with the plaquette operator in the middle, and with these strings on the dual lattice, because we are moving these magnetic fluxes, essentially define the possibility of moving around magnetic fluxes, and I obtain a different kind of symmetry if I close this loop in such a way that no magnetic excitation is live, and this commutes with the Hamiltonian voltage of the Hamiltonian. So, to understand what are the ground states of the system, we have to analyze better the role of these symmetries. We saw that all the closed Z strings on the lattice and all the closed X strings on the dual lattice constitute symmetries of the system. But we must distinguish in the presence of periodic boundary conditions two different cases. The first case is the one of a trivial symmetry, and as I was mentioning before, this trivial symmetry can always be decomposed in terms of the same operators which appear in the Hamiltonian. These operators are called stabilizers, essentially, and you can consider the algebra of all the operators appearing in the Hamiltonian. All of them commute, and all of their product commutes, and this is why, in terms of quantum error correction rules, they are called stabilizers, because all of them have the value 1 on the ground state of the system, because all the Plaquette term in this case have a value 1 for each ground state. But there are also non-trivial symmetries which appear when I am considering periodic boundary conditions, and these non-trivial symmetries essentially amount to create a pair of quasi-particles and moving them around the system on non-trivial loops, loops that cannot be reduced to a point by applying the single Plaquette or vertex operators. And so I have to distinguish strings that are defined by contractible loops, that essentially are trivial and are always equal to 1, and strings which instead are non-contractible and they constitute non-trivial symmetries for the system. If I go back to the lattice picture, you see that you may define essentially 4 non-trivial strings, and you have 2 different strings for each direction. So essentially, you will have this Z2 string, which is the product of Z's along all these edges, which goes around the system because of the periodic boundary condition, and analogously on the dual lattice, the product of the X operators along this string on the dual lattice. And if I consider only strings on the same direction, they always commute because they never share an edge, or they share an even number of edges if I start to bend them and move them around in more complicated ways. But there are also 2 different strings on the other non-trivial loop, again of the Z and X kind. And what is important is that I can essentially consider pairs of these string operators, so let us consider X1 and Z1, and these 2 string symmetries do not commute because they share a single bond, where in one case I am applying a sigma Z and in the other I am applying a sigma X. So we have 2 symmetries that commute with the Hamiltonian but do not commute with themselves. This means that the ground state, usually all the states, are degenerate, so at the same energy equivalent different states. And in particular, with these 2 pairs of non-commuting strings, I may encode, I may essentially describe the ground state by saying that the ground state is constituted by 2 logical qubits that, so I define for each qubit an interspace which is simply 0 and 1 on the basis. And these are eigenstates, for example, of Z1. So I will have that Z1 of 0 on the qubit 1 is equal to plus 0, and Z1 of 1 is equal to minus 1. And then, if I apply instead X1 0 to 1, I go to the state 1, and that's because X and Z do not commute. And I can do this both for the pair X1 and Z1, and for the pair X2 and Z2. So each ground state for this tonic code, so for periodic boundary condition in both the directions, must be specified by 2 sets of states. So that 1 and 2 can be 0, 0, 1, 0, 0, 1, or 1, 1. if you want to understand what is happening in terms of the string operator, so what is the macroscopical description of this system, you may initialize your system, for example, in a set of eigenvalues of sigma x, and this is not an eigenstate for the Plaquette term, but you may apply all the possible strings of the kind z to this initialized ground state in an equal superposition to define what is the ground state of the system. So this is a bit complicated. I'm just answering the question of before, but essentially you may understand these four systems by starting from a square lattice in which you initialize all the spins in the eigenvalues plus, which is up plus down, and I start to apply all the possible loops of strings sigma z. So I will have in the end that this ground state is defined as a sum of all the loop configurations of these z strings applied to the loop, essentially, to the ground state defined by all the classes. And the four different ground states are initialized instead by taking either at the beginning all the classes or all the loops that are topologically equivalent to one string in this direction, one string in that direction, or both of strings which gives a string of this kind. So we can discuss about it later if you're more interested in the structure of the ground states, but I just want you to know that there are these four ground states and they may be labeled by these string symmetries. Actually, you may label them through Z1 and Z2, and you may change their value by applying X1 or X2. One possible question that you may consider is why I am considering only this string and not a parallel one, for example, or a string which is a little bit bent. And the reason is that all the vertical strings of one kind are equivalent up to the multiplication of Plaquette terms. But we know that the Plaquette terms and the ground states are always equal to 1. So if I apply this identity to the string, I obtain a string which bends a little bit, and again, by multiplying it by different Plaquette terms, I am essentially translating my string, but the value of Z2 is equal to the value of all the equivalent strings. And the same is true, of course, for the other strings in the system. So far, we saw that we have the general ground states. On top of this, the general ground states, we may calculate, we may build this electric excitation or the magnetic excitation. And the important thing is that since you move around the electric excitation with strings of the kind Z, and since all the strings of the kind Z commute with each other, you obtain that if you try to create a pair of E excitation and then create another pair of E excitation and move one around the other, you obtain an identity. And actually also if you exchange the position of these two particles, you obtain an identity. And this means that the charge quasi-particles are actually bosons when you consider only them. And the same is true for the magnetic fluxes. So if you exchange two magnetic fluxes, the overall wave function describing your ground states does not take any particular phase. The thing is different instead once you consider what happens when a charge is moved around a magnetic vortex. And in this case, you have that the charge of the magnetic vortex are moved by different strings. So here we have a Z string, and here we have an X string. And if I encircle this electric charge with this magnetic flux, I obtain that the operator that I must apply essentially do not commute either. So I am acquiring a -1 phase that you may interpret as an Arnold phase, or you may also say that if you consider the electric and magnetic charges, they are mutually Abelianians. Essentially, the exchange of the position of two of these excitations brings you a phase which is I, e to the I pi over 2. That's because essentially two exchanges are equivalent to moving one particle around the others. So this is a first example of Abelianians. As I already mentioned, they are always defined as localized excitation, which must be therefore get over the ground state and localized in space. And since they are abelian, we say that their exchange statistics is defined by something which is different from +1 and -1, so they are different from bosons and ferrions. Actually, for the toric code, we have the further complication that it is the mutual statistic that it is different from +1 and -1, so you may also think about the Arnold effect.
Excuse me, in this case you call anyons the combination of E and M.
If you want, if you take a linear superposition of the two, you may arrive to interesting things where the linear superposition is in Abelian actually. But I'm telling you that to define this dynamic model, I have to list all the possible topological charges of my system. And in this case, we have 4 topological charges that correspond either to the ground state, so there is an identity sector which is always present in all the anionic models, and it corresponds to the vacuum. Then we already saw that there are E and M charges, and finally there is also a fermionic charge, which is the simultaneous presence of E and M. Essentially, I'm listing here these topological charges, and you must interpret them as the charges that the subsystem of my system acquire when I look at it from distance enough. Essentially, if inside the subregion of my full system I have, for example, both an E and an M, and I start to do measurement by moving around particles of different kinds, in the end, the only thing that I may understand is what is the total topological charge of this region, and in this case, the total topological charge is psi. So, well, we will go back to this description in much more detail later, but to answer your question, I say that here I have to define essentially an operator which is REM, which amounts to exchanging the position of an E charge with an M charge. So if you look at the plane, we are moving with this string symmetries approximately here and that here, and I want to understand what is the phase that I acquire in this process. And we already demonstrated that twice this phase is mu sign, which is -1 due to this anti-commutation of X and Z symmetries. By the way, here I am representing the system by looking from above and looking at the plane, but another comfortable notation is the one of the work lines, so you must add time, and if you look from one side, you see essentially these work lines of the particles, which will run around the other, and this will be the way in which we will go through the breakthrough, but I don't want to enter in these details right now. However, these exchanges, this operator R, E, M, are called gradings, because of this interpretation of the word lines that weave one around the other without ever cutting. And the important thing is that for the toric code, the only non-trivial phase is the one acquired by an electric charge once it moves around the magnetic vortex, which translates in this relation. The important thing is that the existence of these non-trivial phases that are different from plus or minus 1, so the existence of an operator, of this exchange operator such that a square is different from the identity, is strictly related to the ground state degeneracy. And this is because, as I already told you, you may interpret the previous non-trivial string symmetries around one non-contractible loop and the other non-contractible loop as essentially the possibility of nucleating two pairs of electric charges, moving one around the full system and reannihilating them at the same point. And this is also true for a pair of magnetic vortices moving around the other non-trivial loop in the system. The important thing is what happens once I consider this operator. This operator amounts essentially to creating two electric charges, moving them around and reannihilating them, creating two magnetic vortices in the orthogonal direction, moving them around and then reannihilating them, and do the same process in the opposite direction. If you deform a little bit these operators and you consider the possibility of nucleating pairs of charges and then let the time evolve and reannihilating them, this operator may be represented in this way. So you see that X creates essentially two electric charges, and these are the word lines of the charges that then they stay at some fixed position. Z creates a pair of magnetic vortices that then stay in some fixed position. Then I close this loop by reannihilating the two electric charges, and I close this loop by annihilating the two magnetic vortices. And essentially we obtain that the result of this operator is depending on the commutation between the Z symmetries and these X symmetries, so it is equal to -1. But this process can be topologically deformed in a process in which essentially I wind twice any and an M charge one around the other. So it is exactly the operator R squared that we were considering before. So if there exists a pair of excitations in your system such that this operator R squared is different from the identity, it means that you have a couple of string symmetries that do not commute with each other, and again, since we have symmetries not commuting with each other but commuting with the Hamiltonian, we obtain that the ground state must be degenerate. So essentially what I'm telling you is that every time you have abelian unions, you get some degeneracy on the torus because of the existence of these string symmetries which do not commute. So now let us summarize a little bit what we saw for the toric code. We saw that there are 4 ground states that are separated by a gap. This gap is 4 actually, from all the high energy excitations. So you see that the spectrum matches the one that we were considering at the beginning to have topological order. We saw that the ground state degeneracy is depending on the existence of these string symmetries along non-contractible loops. So that we have a correspondence on the number of non-contractible loops and the number of ground states. Actually, each pair of non-trivial contractible loops, non-contractible loops gives me a degeneracy 2. And on the torus, since I have 2 different sets of non-contractible loops, I have a degeneracy to the genus of the torus, which is 4. And so we have that the degeneracy of these ground state manifolds depend on the topology of the system. There is changing the boundary condition or introducing producing holes, we will change this projects. And furthermore, we analyze what happens when we apply local operators. Local operators are idle elements of the stabilizers, so they do not change the energy of the system, but they do not change either the ground state in which you are, because we saw that applying a closed string symmetry in a small subset of the system, such a way that it is a contractible loop, does not do anything on the ground state, because it's just equal to 1, or the local operators move the system from the ground state, from the excitation, if we apply an open string symmetry or a set of disjoint strings. So essentially we fulfill also the second requirement for having topological order, which is that no local operator may allow transition between one ground state and the other, and in particular we have also local observations cannot distinguish the ground states. And finally, in the toric code, we saw that there appear a first example, even though it is a bit tricky example of abelian anyons due to this effective out-of-bond phase of electric charges moving around a magnetic vortex. So I don't know if you have questions so far, or maybe we can have a break of 5 minutes right now, and then we continue the talk. Break and then we
yes, very good.